We're live.
Okay, great. I think we need to hit something here. Sorry. I guess I'm not ready. I'm gonna acknowledge it on your phone. Okay. Thank you everybody for joining us at our next annual meeting. For the end of our first day, we have an exciting speaker, Dr. Jason Barnes, who is a professor of physics here at the University of Idaho, one of several planetary scientists here at this university. I'm a Titan scientist, and I'm really excited to see this talk. I'm really excited about what he's going to talk about, which is the Dragonfly mission. Jason has been working on Titan science for a long time. He went to Caltech. You got your BS in astrophysics, is that right? Or
astronomy.
Astronomy, okay. And then he did his PhD at the University of Arizona. And I actually remember him talking when I was a grad student at the University of Washington about sand dunes on Titan, or I guess they're Poland dunes.
Had me out to give a talk. That's right.
Yep, exactly. So without further ado, I'll let you get started.
All right. Well, thanks, Darcy. Darcy and I worked together for many years on the Cassini mission, and today I'll be talking to you about the next mission to the Saturn system and to Saturn's giant moon Titan, which is called Dragonfly. And Dragonfly is a bit different than Cassini, okay? Cassini was an orbiter mission that orbited around Saturn and would fly by Titan periodically to take pictures and acquire magnetometer data and that sort of thing. Dragonfly is going to sort of build upon what we learned from Cassini, and we're going to go and land on Titan's surface and get around there. And we were thinking of how we'd get around on Titan. Do you want to get around on Titan using wheels like the rovers do on Mars? And so we thought about that, but we kind of want to land in Titan's sand dunes. And you guys ever been off-roading in sand? Okay, I don't recommend it. There's no way to air the tires down once you get up to Titan, okay? So we decided instead of using wheels to drive around, we were going to fly around using rotors as one single giant quadcopter. Actually, it's an octocopter. It's a dual quadcopter. We have 8 different rotors. So I'll tell you today about, a little bit about Titan and a little bit about the mission. And please ask questions if you have them as we go. I like questions. So more the merrier. Okay. So just to orient you, make sure this is working. Here we go. Just to orient you, Titan is a moon of Saturn. Saturn is way out there in the solar system, right? It's 10 astronomical years from the sun. So it's cold out there. But sunlight there is only 1% as intense here as it is here at the Earth. So everything out there is pretty cold. Saturn is a gas giant, of course, like 8 Earth diameters across. But Titan is much more close to a planet you could imagine. Okay, Titan is about a third the radius of the Earth, so it's about the third the size of the Earth, and it's the second largest moon in the whole solar system. But one of the coolest things about Titan, if you ask me, is that it's one of only 4 places that we know of, in the entire universe that have both a solid surface and a thick atmosphere. Okay, right? There's plenty of places out there like Saturn. Okay, that's a gas giant. It's air all the way down. All right, there's no solid surface anywhere. And then there's plenty of places like asteroids or Mercury or the moon, which have no air but have a nice solid surface. But if you're looking for places that have that complexity of sort of rock-air interaction that we get here on Earth, there's only 4 places you can find it, and those are Venus, Earth, Mars, and Titan. And of these, Titan is in some ways, a lot of ways, I think, the most Earth-like, okay? One of the ways it's not the most Earth-like is the temperature. So if you guys are familiar with the Kelvin scale, like it's 94 Kelvin at Titan. 77 is liquid nitrogen. So we're above liquid nitrogen, but like not by a whole lot. These other planets Mars is probably the closest to Earth in terms of temperature. But if you look in terms of, for instance, its atmosphere, Titan's atmosphere is by far closest to Earth. We measure atmospheric pressure in a unit called the bar, which is the same as the pressure at sea level on Earth. And in that scale, Venus's atmosphere is 92 times thicker than Earth's. The pressure at the surface of Venus is the same as the pressure at the bottom of Earth's ocean. Okay, so it's a pretty hostile place. Similarly, the pressure at the surface of Mars is 200 times thinner than Earth's. So there's not a lot of air there. In fact, there's so little air there, you need a spacesuit just to keep your blood from boiling in the low pressure. But Titan's atmosphere is just right. It's 1.5 bars. It's a little thicker. It's a little, thicker than what's in this room right now. But if we were to close this room off and pressure it up to 1.5 bars, you'd be fine. You can totally survive in 1.5 bars. It's not too big a deal. Also, Titan's atmosphere is most similar to Earth's in terms of its composition. Anyone know what we're mostly breathing in this room right now? Nitrogen. That's the same thing on Titan. Titan's atmosphere is also mostly nitrogen. And these other two planets, Venus and Mars, have mostly carbon dioxide atmospheres. So Titan is also the most similar to Earth in terms of the composition, and then it's mostly nitrogen. Now, there's no oxygen in Titan's atmosphere, but the number 3 constituent of Earth's atmosphere, most days, it depends on where you are on the Earth, is water vapor, actually. And so there is a chemical on Titan that sort of plays the same role that water vapor does on Earth, and that's methane. So methane is the natural gas that comes out of your stove that you light and has that blue flame, okay? That's what happens when you burn it. But if you cool it off down near 90 Kelvin, methane is near its triple point, where it can be a solid, a liquid, or a gas if you change its conditions just slightly. And so on Titan, methane forms clouds, and those clouds rain, and that rain carves the surface into channels and leads into lakes and seas of liquid methane at the poles. So Titan, in that sense, is, I think it deserves to be upgraded to be with these big boys. It's one of the very important places to explore in our solar system. In addition, Titan also has a prominent role among this other group, cadre of colleagues in the solar system, and those are the ocean worlds. So it was only about 25 years ago that we realized that liquid water is ubiquitous in the solar system. Okay, it's all over the place. When the Voyagers flew by the icy moons of Jupiter and Saturn and Uranus and Neptune, they took pictures and they're like, wow, very exquisite frozen ice cubes. Great. But when we went back with the Galileo spacecraft, it flew next to Jupiter's moon Europa here and realized that Europa was affecting Jupiter's magnetic field in such a way as to reveal that there is a conducting layer of material inside Europa. Now, either a bunch of students went there and covered it in aluminum foil as a joke, or there's a salty liquid water ocean that's conducting electricity beneath Europa's crust. And so we now realize that what we thought were these dead ice cubes in the outer solar system, many of them are in fact ocean worlds that have far more liquid water even than the Earth. And among these are Europa, as we mentioned before. Jupiter's moon Ganymede is even bigger, and we think has even more ocean. And of these, Titan may have the most liquid water anywhere in the solar system. And this is particularly interesting at Titan because we think that there are 3 things, as astronomers, okay, we try to take a step way back. We think there's 3 things you need for life, okay? Energy, carbon, and this is water in the middle here, okay? So we think there's plenty of energy out at Titan despite the low intensity of sunlight. There's water, at least beneath the crust, but where Titan really shines is in the existence of carbon. This methane that's in the atmosphere I talked about is CH4, 1 carbon and 4 hydrogens. And when solar ultraviolet comes in and smashes that methane and breaks it up, it will reconfigure into more and more complex molecules that cover the atmosphere in haze and eventually cover the surface in organic sludge, in organic goo. And so what we'd like to know is what happens if that goo manages to get in contact with liquid water over time, because we think this may enter into a situation maybe similar to the early Earth, where you had liquid water, you have organics in the atmosphere produced by lightning or other processes, or photochemistry perhaps. What happens when you combine those? Well, life eventually arose here, We don't know if that it would happen on Titan or how far it might have gone down that path, but that's what we want to find out. That's why we want to visit Titan, and that's why it's such an important target. Okay, so these are two competing pictures of Titan. The one on the left is the view that you would see with your eyes. Yeah, doesn't look like much, okay? That organic material that gets photolyzed in the outer atmosphere builds itself into particles about a micron in size that fill the atmosphere. So looking through Titan's atmosphere is like looking through the atmosphere in the Pacific Northwest in August during smoke season, okay? This stuff is like smoke. So imagine that Titan's whole atmosphere is filled with this smoke all the time. You can never see through it with your eyes. The view on the right is a view that we compiled from Cassini data, looking at longer wavelengths that can see through the haze down to the surface. And so this is what Titan's surface looks like if you were to look all the way through, although, you know, with infrared eyes. So imagine you're a boat or something. Okay, so this green stuff we think is water ice, but covered with this organic stuff that's coming out of the atmosphere. All the brown areas near the equator here, we now know are sand dunes. And the sand on Titan is really interesting. We'll talk about that in a bit. Here's an impact crater called Synlab. These are Tui and Hote ratio right down here, which we now know are old, dried up seabeds that are covered in organic evaporites. And our mission will be landing right south of this crater, Selk crater. We'll be landing right here in 2034. So that'll be awesome. Okay. So yeah, question.
Yeah, I'm still stuck on the previous slide. So,
Yeah.
so the water's frozen now.
Yeah, 94 Kelvin.
That's why none is in the atmosphere.
Exactly. So at 94 Kelvin, in fact, it's so cold, the water is, you know, you don't even think of it as a glacier because glaciers flow because they're sort of near their melting point. This is like rock.
Yeah.
So this is water, but it behaves more like basalt.
Oh.
Yeah. But you're right, it's not liquid today. So how can you get these organics on the surface to mix with liquid water then? Well, there's two ways we can think up to do it, okay? One is to bring the liquid water up from below, and the second is to make new liquid water afresh. So we'll be visiting this crater called Selk crater. So this is about 80 kilometers across, so it's pretty big. It was created by an asteroid or a comet that was probably about 4 or 5 kilometers in diameter and smashed into Titan in at 16 or 20 kilometers per second. So those of you remember their high school physics, what's the equation for kinetic energy?
Half mv squared.
1/2 mv squared. Yeah. Okay. So
Good job, guys.
you can imagine you're astrophysicists now. Okay.
Yeah, they're physics.
Exactly. Excellent. Okay. So pitch properly. So you can imagine if you have a 4 kilometer diameter ice cube, M is quite large. Okay. Now you're moving at 20 kilometers per second. And then you square that. Okay. The result is why we refer to numbers as astronomical. Okay. This has a tremendous amount of energy when it comes in. And the bulk of that energy, the majority of that energy actually goes to melting the target rock. So most of that energy goes into heat and melts what's on Titan, the target rock, is water. And so we think that there should have been a liquid water melt sheet at the bottom of Selk crater, maybe up to 100 meters deep, that could have remained liquid for thousands of years. And so that's what we want to visit. We want to see what happened when that melt sheet was created at Titan's surface, mixed with all these organics in the atmosphere and possibly in the surface itself, and then just sat there for a couple thousand years. What pathways has that organic chemistry taken, all right? Is it on the path toward life? Is it created its own self-replicating molecules already? We don't know, and that's what we want to find out. So we're going to be landing. If any of you have visited Meteor Crater in Arizona, you know it's probably not a great place to drop your lander. It's pretty rugged, okay? So we're going to land down here in the sand dunes, which we think are going to be pretty benign in terms of a landing site. And then we'll hop over to the crater to get to these previously liquid sediments to be able to sample them and see how far chemistry has progressed on Titan and whether or not our ideas about the formation of life from abiotic organic chemistry are on the right track or not. Yeah.
How long will it take from landing to get to the crater?
Right, so we can fly, maybe 15 kilometers on a single hop. And this is about 150 kilometers. So it could be 10 hops if we just went as fast as we could, but that's not how we're going to do it. We're going to employ this strategy called a leapfrog, where we kind of don't want to land in sites that we don't know are safe. So what we're going to do is we're going to take off. We're going to fly out 2/3 of our range, like 10 kilometers. We're going to take pictures, okay? Then we're going to fly back 5 kilometers and land at a site that we previously scouted. And the next time we're going to go up 10 and back 5, and up 10 and back 5, and up 10 and back 5. So we'll always be landing in a spot that we've already looked at, that the engineers agree is safe, the scientists think are interesting. And so that it'll take a little bit longer. And we fly once a month, once an Earth month, or once every 2 Titan days. So our total mission is about 3 years and 4 months. And so how long exactly it takes will actually depend on where in our landing ellipse we fall. Titan's thick atmosphere and low gravity make it so that we're going to be sitting on our parachute for a long time. And so if there's a slight drift with the winds, we'll end up, going in a different direction. And so we could end up one way or the other. So somewhere between 1 year and 3 years is what we expect. So that was a long answer to a short question. Yeah.
We're probably gonna get into this later, but what's the power source of the drone?
Yeah, so what are we powered by? Well, we're way out in the outer solar system. Sunlight's 1% as strong, and then you get it through all that haze. It's another 10 times dimmer again. So it's only 0.1% the amount of power you get from a solar panel that you get on Earth. So you need solar panels like the size of a tennis court.
Yeah.
And then not very good for flying. So we are actually powered by what we call a nuclear battery. It's a radioisotope thermoelectric generator. So this is the same power source that Cassini used, the same one that the new big Mars rovers were using. The Voyagers that were launched in 1977 when I was born, okay, are still going, powered by plutonium-238 out, beyond Pluto in the outer solar system. So this is a very low amount of power, but it does last for a long time.
I was gonna say, don't forget about the Martian. I feel like that's how most.
That's right. That's right. That's how Matt Damon didn't freeze when he was sitting in the rover.
Yeah.
The radiation dose probably wasn't that big. So in addition to liquid water, Titan is the only other place we know of that has liquid sitting on the surface. These are some pictures of some of Titan's clouds. So these right here are some clouds, thunderstorm clouds near about 40 degrees south on Titan. So about the same latitude as Idaho, but further down. It's doing it on its own.
Yeah.
And so there are storms and clouds and rain on Titan, but it's not very common. Okay, at any given time, 2 to 3% of Titan might be covered in cloud. You want to guess what fraction of Earth is covered on cloud at any given time? Yeah, about 70. Yeah, that's right. And if it's in the Pacific Northwest in the spring, it's more like 98. So yes, Titan has clouds, but they're not all over the place. And on any given place on Titan, on average, it rains once every 1,000 years. So it's not like raining all the time, but it does rain enough that rain is the primary source of erosion on the surface of Titan, and that's the only other place other than Earth that's true. We actually have pictures of some of those erosion channels taken by the Huygens probe. So the Cassini mission carried with it this probe that was designed to go through the atmosphere, and as it was flying down through the atmosphere, it took pictures as it went. It took a sequence of pictures that we've recreated into this 3D view here that shows these rain channels that seem to have been carved by liquids falling out of the sky uniformly across the surface. This is the only other place in the solar system, in the universe, that we know where this happens. Okay, there are channels on Mars that don't look like this. They don't look like they've been formed by rain. They look like they've been formed by groundwater flowing out. Okay, so this is a really exciting similarity between Earth and Titan. And in fact, this Huygens probe, because Titan has such low gravity, 1/7 that of Earth, and such thick air, under its parachute was able to just land and survive after it landed. And here is a picture of what the surface of Titan looks like. How awesome is that?
So
That is
awesome.
so amazing.
That is amazing.
Okay?
How many
Like, this
people
is-
have seen that picture?
I know, this is just like, how many planets do we have pictures of from the surface? I think it's Venus, Earth, Mars, the Moon, and Titan. Like maybe the comet that the Europeans landed on.
Yeah.
Maybe that counts. So we have very few images from the surface of any planet, and so that's why this is so exciting. Okay, we have this picture from the surface of this ocean moon in the outer solar system, and what we think we're looking at here is there's a little granular material near the lander here. And that may be related to the sand, or that may be broken up material that's been broken out by the channels that we saw that were a little bit nearby the landing site. The lander had a lamp on it, so this is just the spot that it's illuminating, and the rest of it is illuminated by the sun. And then there are these little whitish rocks in the distance. Those are about 10 centimeters across, so about the size of your fist. And we think they're made of water ice. I mean, that's a supposition. We don't have spectra on them yet. But what do you notice about those rocks?
They're smooth.
They're smooth, they're rounded. Yeah, exactly right. If you see rocks on the moon, they do not look like this. Okay, they're extremely angular because they've been blasted out of an impact crater sometime in the past, and they're just all jagged.
They also seem to all be similar size, which I find interesting.
Yeah, no, very good point. So they're sorted in terms of their size and they're rounded. And both of those observations are consistent with these having been transported by over surface flow of liquid methane from a rainstorm that's come through one of those channels. Is able to carry, based on the speed of the flow, it's able to carry particles of a given size and dump those out at a given point, and it's rounded off the sides. So in addition to being, awesome from a science point of view, if you look at it from an engineer's point of view, okay, the engineers don't care what you want to learn. They want to land on the flattest, most boring parking lot on the entire planet that's safe. And you know what? This lowers their blood pressure, okay? We can see that there's lots of plenty safe landing sites. These are not dangerous rocks that are going to tip a lander over or anything, okay? So when you show pictures like this to the engineers, this picture, in fact, specifically has enabled our follow-up mission, that we know safe landing sites are out there. And that's not true, for instance, at Jupiter's moon Europa. We're considering a mission there, but we have no idea what it's going to look like. There'd be like ice spires everywhere that you're going to have to land on. And so they have to design a really complicated landing system. Whereas at Titan, we know that safe sites exist, and we just have to find them. Okay, so this is a picture in the infrared taken looking down on Titan's North Pole. So the North Pole of Titan's like right here, okay? These dark splotches are the lakes and seas of liquid methane, and they are concentrated at the poles because the poles are the cold part of Titan. They're the cold trap, okay? The same reason we have our ice caps at the poles of the Earth, which seems obvious, and I wish if you can time travel, please tell me that 20 years ago so that I could predict it and look like a genius, because no one thought this was going to be true until we got there and saw it, and they were like, oh yeah, we should figure that out. So this one is called Kunga Mare right here. This is Ligeia Mare, and this one over here is Kraken Mare. It's the biggest lake on Titan. And we've been able to, skip too far, sorry. So those lakes may or may not be producing some of these organic materials that we see near the equator. This is a view of those sand dunes I talked about that are near the equator, but this view is in the radar. It's a view with radar, so it looks a little funny. That's why it's black and white and looks kind of splotchy like this. But these long, black, dark streaks here are the sand dunes. And these dunes are about 100 meters high, and they're about 3 or 4 kilometers between each dune. And they go on for hundreds of kilometers in the downstream direction, which is amazing because those dunes are almost the exact same size and shape as the sand dunes in Earth's biggest deserts. Okay, like the gravity's 7 times lower, the temperature's 1/3, the atmosphere is denser. Why are these dunes the same size as the ones on the Earth? I don't know. If you know, let me know. We'll write a paper. Okay. But because they're so similar in size, I was able to visit some of them to try to get a sense for what these dunes are going to be like once we visit them. So these are the sand dunes in the country of Namibia in Southwest Africa, and they are about 100 meters high. I had to climb them, so I know they're high. I mean, climbing a sand dune, right? Every step you take, like you come back, 2/3 of a step. It's pretty exhausting. And they go for just as far as the eye can see, tens of kilometers, hundreds of kilometers. This is looking south in this particular case. And then they're separated over here by the next dune. And in between is an area called an interdune that has no sand in it. And this is not how it looks in the movies. Okay, you look at Jakku in Star Trek or Star Wars: The Force Awakens. Okay, it has sand everywhere. Okay, but that's not what actual sand dunes look like. This and the Sahara and the Arabian Desert typically have about half coverage of sand by these dunes, and the other half are sand-free interdunes right in between them that are just showing bedrock or whatever is down there. In the Namib here, it's gravel. So this is why we want to land in Titan sand dunes. We think we'll be able to sample the organic sands, but also be able to get to water ice just a couple hundred meters away with a really short hop pretty easily. And that's the genesis of this idea, which is a lander that's pretty big. This thing is pretty large, but we will land in the sand dunes. We will sample both the organic material and the previously liquid water. It's now, of course, long frozen, both in the inner dunes, and we'll eventually head over to this crater to find the stuff we know was previously liquid. So that, in general, is the plan. We're carrying 4 scientific instruments. Our flagship instrument is a mass spectrometer that will tell the composition. This isn't quite a Star Trek tricorder that'll tell us everything, okay, but it will tell us the size of the molecules present on Titan that will allow us to see, does it have amino acids, which are the building blocks of life? Does it have nucleobases or lipids? What kind of organic molecules have formed on the surface of Titan? And how far have they progressed toward prebiotic chemistry or possibly even biology? The way we sample material is we have, all right, well, I'll give this away. Okay, so this is the size of the vehicle. This is my former student, Shannon McKenzie, who's now the assistant project scientist for the mission. She works at APL. For scale, it is big. This thing is big. I say quadcopter, you think that thing that you got from your uncle on Amazon that flies around the room or something. No, this thing is the size of a small car. It's about 4.5 meters long and a little less than 2 meters high. And it's got these drills on either side. So the way we sample material on Titan is the same way you sample material in your living room carpet, okay? With a vacuum cleaner. So these are the blowers. These suck from material through these tubes from the drills, one of which is on each skid of the lander. So we have 2 choices as to where to drill. And that sucks up the dirt and moves it into the mass spectrometer carousel up here that does the sampling and measures the composition. And then poops the rest of the extra out onto the surface bed over here. So this is kind of cool, okay? We've done sampling on Mars, and they have these arms, right? They scoop it up, and on the Mars Phoenix mission, they scoop material up, and then they went to dump it in, and then dump it, and it got stuck in there, okay? It was more cohesive than they thought. Mars only has 1/3 the gravity of Earth. It wasn't helping, okay? This is a really robust sampling system that we think is really going to really work well. And the only places it works are Earth and Titan. I mean, I suppose it would work on Venus, but then your sampling system's kind of like a flamethrower pointed inside your spacecraft, because the temperature on Venus is 700 Kelvin. So,
Can I ask a mid-talk
yeah,
question?
oh, please.
Is it designed to take as many samples as you want, or is it designed to take a limited number of samples?
Yeah, so there are these little sample cups in the carousel up here, and they're about, okay, we're in phase B, so it keeps changing. I think there's like 28 or 30 cups that we'll be able to use. Some of them have derivatization agent, like the ones on Mars, to be able to sample larger molecules and see what they're doing. So there's a limited number of fresh cups. Okay. But once the cups are used, you can just dump the stuff out and use them again. There might be some cross-contamination. But one of the advantages of being on the surface here is that we just can get so much sample, right? We just run that vacuum and we can get, cubic centimeters, as many cubic centimeters as you want. And so we're pretty confident that even with the dirty cup, we can overwhelm the old sample with new sample, and we'll be okay. So there are a limited number, but of just of clean ones. So eventually we should be able to just keep running this and keep running them and I don't know what will be the end of it, but it probably won't be the number of cups. Okay, so that was one of our instruments. Another instrument is a gamma ray neutron spectrometer. This pumps neutrons into the surface and listens for the gamma rays that come back from when electrons get knocked out of atoms. Okay, and those are characteristic of which type of atom they are. So the gamma ray neutron spectrometer is measuring the elemental composition, like how much carbon is in the molecules down there, how much hydrogen. The mass spectrometer measures the size of an individual molecule, right? Like how big a molecule is and what it might be made of. And so these are very complementary, right? This is measuring everything within a couple meters of the lander. This is measuring everything, in just that cubic centimeter that we drilled and sucked up. And so these are our complementary instruments we have to measure surface composition. We have 8 cameras. We have 2 looking forward. We have 2 up on our radio dish here, which is a flat phased array that's communicating back to Earth. And those 2 cameras up there are stereo cameras that, because they're on the dish, they can be turned around and we can build up panoramas of the entire landing site. Then we have 1 camera on each side looking at sort of our workspace cameras, kind of looking down at the skids. Then we have 2 super high zoom cameras looking just at the drill site itself. That's we call it's like the Mars hand lens imagers. It has super tiny pixels to be able to image individual sand grains and see how big they are, how rounded they are, and what their distributions are. And then we have our last instrument is the geophysics and meteorology package, DragMet, and it's measuring the atmospheric temperature and pressure, measuring the weather, and it also has a seismometer on board. We have no idea what the earthquakes are going to look like on one of these ocean worlds that has ice on the outside and water on the inside, and then rock, presumably further down. And so we're going to, for the first time, be able to measure how frequent earthquakes are and what might be causing them. And if we get a big enough one, we'll be able to use it to probe exactly how deep the ice shell is, how deep the water ocean is. And a really big earthquake will allow us to actually probe the entire interior of the moon of Titan, which would be really exciting. So yeah, it's big. I say it's big, it's big. Our rotors are about the same size as a Cessna rotor. And we have 8 of them. Okay. We have our total mass is about half a ton, so 500 kilograms. So who's seen the picture of the Mars helicopter? Okay, that's cool. Okay, its rotors are the same size as ours.
Really?
Yes.
Because there's so little atmosphere.
Yes.
Yeah.
That thing masses 1 kilogram. We're 500 kilograms. Okay, so that is a little toy. It can fly for 90 seconds before it runs out of power. We can fly for half an hour. So we have much bigger rotors. This is a much bigger vehicle. This is much more like, we really think of it more as like a Mars rover. We have everything with us, all these different components, a lot of scientific instruments. We can move them all around the surface so that we really consider ourselves a relocatable lander more than anything else, right? So we're a lander. We spend almost all our time on the ground doing science. And then we fly once a month to be able to get to a new site. And this is Elizabeth Turtle, the principal investigator of the mission. I'm the deputy principal investigator of the mission, so sort of like the vice president. What that means.
So is there concern that for the prop wash to create cross contamination of the sample?
Yeah, so certainly as we turn the rotors on, we're going to start blowing material away, especially if we're on a sand dune of unconsolidated material, stuff like that. We've calculated we should be able to be eroding at a rate of a couple centimeters a minute. So it's not too bad. In fact, we're going to use that as a feature. One of the things we want to know is what the threshold is beyond which material starts to saltate around. The sand grains start to move on Titan. And one of our experiments would be to turn on the rotors and slowly crank them up and see when the sand starts to jump around. As an experiment to be able to constrain our sand and our dune formation model. So There will be some, but because we don't actually have to produce all that much lift, right? Because gravity is 7 times lower. It's the amount of surface erosion and the probability to create a huge dust cloud actually isn't all that large. We don't plan on hovering right above the ground very often.
Do you anticipate any flying in wind or wind being a thing?
Yeah. So because Titan's atmosphere is so thick and the sun is so feeble out there, typical winds on the surface of Titan, as inferred from the Huygens probe, are at the several tens of centimeters per second level. So like this. Okay. Like the real big winds that are moving the sand around, we think might be as fast as a meter per second, maybe 2 at the outset. But we fly 10 or 12 meters a second. So we do think there will be wind. We don't think it's going to be that big a deal, and our guidance and control algorithms are designed to be able to compensate for it and put us down safely, we hope. But that's also why we have skids, right? Same reason helicopters have skids, because that way you can have a little bit of velocity in that direction with the skids, and you're not going to catch on a rock or something and tip over. That's the idea. Yeah.
Is the travel going to be autonomous like the Perseverance rover, or are we going to have to check on it?
So it's 80 light minutes away out at Titan. So, and the flights are like half an hour. So we have to upload everything it's going to do. And it does, however, have some onboard smarts. So it takes pictures as it's flying and compares those pictures to the previous pictures, so it can tell if it's drifting in the wind and whether it's found the same site that you told it to go to from the last flight. We have an onboard radar and LiDAR. LiDAR is light radar, right? We send off laser pulses and measure how long it takes them to get back. So you can build them an instant digital elevation model of your terrain around you to be able to find a safe landing site. So we have a combination of autonomous and commanded. It's definitely going to do each flight on its own, but in between those flights, we're going to look at all the data and sort of tell it where to go at X and give it hints as to where to go and try to evaluate what it's going to do next. Yeah.
So is there going to be like a satellite communications relay in orbit, or is this thing going to be communicating directly on that 80-minute delay?
Yeah. Communication satellite would probably cost us an extra $500 million. So we're going direct to Earth. That's right. And so it's just this little dish, this little 1.3 meter dish, about this big, right? That's on our back. We carry it on our back, fold it up. Once we land, we fold it up, and we're able to communicate back. But certainly, I mean, if you guys have seen the Mars landings, they had this amazing HD video of the entire landing from orbit. Okay, we're not going to have that because we don't have a fleet of 4 orbiting communications relays with 4-meter dishes, only 1 AU from Earth. Okay, so we really are going to be data limited. Our total amount of bandwidth we get back is about like a CD worth of data per year.
Oh my God.
Okay, like Mars gets that in a couple hours. So we are limited in the amount of data we can send back because we don't have that relay. But that's also what enables us to do this on this is a medium NASA mission with a PI managed cost cap of $850 million. So that's medium for us.
And you said the day length there is like about 15 Earth days.
Right.
So when it's not facing Earth, you just can't
do anything.
Yeah.
Yeah. So Titan rotates once every 16 Earth days. So during the Titan night, we actually use our radioisotope thermoelectric generator, the nuclear battery back here to charge our lithium ion battery. Is what we actually fly on. The nuclear battery only provides about 100 watts of power. So like well less than your laptops here. But we're not doing anything else overnight for 8 Earth days. So we slowly charge up that big battery so that come Titan morning, we got enough power in our big batteries to either fly or communicate back to Earth or whatever we have to do. So that's sort of our power strategy. Yeah.
Is there any thoughts about like storing some extra data on board in case there's another Saturn or Titan orbiter that you could send higher rates of data back?
I wouldn't say that's why we're doing it, but yeah, I mean, like nowadays you can fit 100 gigabytes of data on a chip the size of my pinky finger. Okay, so our plan is to take way more data than we're actually going to be able to send back. We'll just store it on board, and we'll send up thumbnails, right? And if it looks like, oh, okay, looks boring, we won't bother to send it back. But then if 6 months later, some grad student says, wow, can we get those pictures back from that one landing site 6 months ago? We'll be like, yeah, sure, it's still there. So it's sort of like you know, an external backup hard drive here that'll just be sitting there, and we can uplink it whenever we want. But it's real easy to store all those data, and it's real hard to send it back. So that is a limiting factor to be somebody you can send back. But we'll be able to keep them there for future reference and future use. Okay, so because we're in Idaho, I like to talk about the nuclear battery because it's going to be built here. It's going to be built at the Idaho National Lab. This is where these things get built. So the way these things work is they have plutonium-238 in them, and this is not a nuclear reactor, okay? It's just radioactive material, radioactive plutonium-238. It has a half-life of 88 years, and as it decays, it creates heat. And that heat is at the center of these radioisotope thermoelectric generators. And then you have the fins on the outside that create a cold side. And in between, you put what's called a thermocouple, which is an electronic device where if you heat one side and cool the other, it produces electricity very inefficiently, about 7% efficient. But no moving parts. So it can live for 50 years. And this is the actual RTG. These are infrared images, the actual RTG on Perseverance, which is now on Mars, which landed last year. I got to visit Idaho National Lab in about 2010 when the RTG for the previous Mars mission Curiosity was being built, and they let me see it. Okay, first of all, you had to put your phone away, and it was like going through the airport security where they look for all the metal on you, but they didn't give it back. So then they give us the tour, and they said, "You want to see it?" I was like, "Yeah, I want to see it." Okay, so they got this door. It's about like 25 centimeters thick, steel reinforced concrete. They slide it open, and then you can see the RTG in there. It's still got plexiglass around it. Okay, we could see it for a couple seconds, and they slide it. But that actual RTG that I saw is on Mars, which is kind of awesome. Okay, and we're going to have a similar one that they'll start fabricating for us in the coming years here, getting ready for our launch. So of course you can't fly with rotors out to Titan. So we're going to launch. This is actually our old, I need to update this slide. This is our old flight path through the solar system where we're going to do a bunch of gravity assists before getting out there. NASA has pushed our launch date back. We were originally supposed to launch in 2025 and they pushed us back to 2027, but they made it up to us. They're going to launch us on a heavy lift rocket. So we will actually get there about the same time as we were originally going to get there, even a little earlier. And we will fly out and then do a rocket burn, and we'll have one Earth gravity assist launching in June of 2027, and we'll arrive sometime, 2034 or below. Before, it depends on the details of the trajectory we end up with. Yeah.
I'm sorry, what's a heavy lift rocket?
Yeah, big.
It's a bigger rocket.
I can't tell you what it is because we don't know. What happens is NASA will put this out for bid, and they will pick the best bid for the government in terms of money and capability and risk and that sort of thing. A Falcon Heavy, for instance, would meet our requirements. So would an SLS? I don't think that would be cost competitive, but I don't know. We'll see what happens in the bid. It will be an open bid.
Yeah.
And so whoever has the best option to get us out there will win. And that competition will happen in the next couple of years. So we don't even get to decide. We just tell NASA what we need, and NASA puts out this open bidding call so that it's a fair and open competition. We'll see what we end up with.
Nice.
So after flying through space for 7 years, we will be arriving at Titan, and this is what it may look like. This is a video. We're going to slam into the atmosphere at 7 kilometers per second, which is actually pretty slow. I mean, Earth orbit is 8 kilometers per second. So this is a pretty benign entry. We will slow down using our heat shield and start deploying parachutes. If you've seen a Mars landing, you've seen JPL calls it the 7 minutes of terror. Okay. Well, with Titan's thick atmosphere and low gravity, really for us, it's an hour and a half of mild concern. So we eventually arrive in the lower atmosphere after an hour and a half, where we'll ditch the heat shield. And once we get to about 4,000 feet elevation off the deck, we will do what we call deployment and transition to powered flight and turn on the rotors and start flying. Now, this first landing is the one we won't have been able to scout, okay? So the vehicle has to find its own first landing site. And so it will fly across the dunes, looking for an area that has less than 10 degrees slope and is far from killer rocks, which are ones that are about 25 centimeters in diameter. So it will use that LiDAR and its radars and its cameras to fly around and find a landing spot. So this is different than what we do on Mars. Older Mars landers, they would just literally take pictures of the whole landing zone and say, okay, it's a flat parking lot, let's send it there. The Perseverance lander is very sophisticated in that they took pictures of the entire surface they were going to land on with resolution of about 30 centimeters. And they found all the rocks and they told the rover where all the rocks were. So once it came in and knew where it was going, it automatically targeted itself around them, but it didn't have to find the rocks. So we have to find the rocks and find our way around them. But the nice thing is we don't, everywhere in the landing zone doesn't have to be safe, right? There just has to be a landing safe zone that is safe that we can find within the half an hour or so before our battery runs down. We're very confident that we'll be able to do that. Although I admit it will be a little nerve-wracking when this finally happens. Okay, so yeah, we're gonna fly a nuclear-powered interplanetary quadcopter on a moon in the outer solar system. And the science we're gonna do is we're gonna try to measure the composition to figure out how far that organic material has gone toward formation of life. Whether or not there are environments that weren't habitable on Titan with the liquid water that was after we hit with the impact crater. And we actually will have the capability to do some rudimentary searches for chemical biosignatures to tell whether or not these primitive chemical processes may in fact have evolved into simple self-replicating molecules that might be life or precursors to life. So it'll be really exciting, and I hope you guys will be with us, and I'll be able to give you another talk come 2034 about what we found.
That talk was so good, we might ask you to talk every year.
It was a little different than last time, right?
Just, yeah, you know, definitely more different details.
Yeah, I just talk about whatever. Yeah.
Is it too
So
late?
much complexity to it.
Is it too late to call it an octocopter? Because it has 8.
It does.
Why is it called 4?
Well,
Or
it's called the
quadcopter
dual
then?
quadcopter because it's
Dual
over 100.
quadcopter.
Oh, but
Yeah.
octocopter has such a great ring.
Yeah, I think it is it's totally okay to call it an octocopter. It is
Okay.
an octocopter. It's also, we call it a dual quadcopter for that reason. In fact, so on each stalk here, we have contra-rotating propellers that each rotating the opposite way, so that they each have, they count their angular momentum counters out. You guys have done angular momentum experiments in your early classes. I don't know if you've done the bicycle wheel experiment. Okay, yeah. We don't want to do that with the spacecraft. Okay, so that's why it's got each of those rotors goes the opposite way, so it has net zero angular momentum. It's easier to maneuver.
I'm a physics professor and I built an airship out of a big balloon and I didn't think about that. Yeah, I turned it on. It was just like,
It just started. It